This is section 2.4, part A, finding zeros of polynomial functions. The I can statements for this section: I can find real zeros of polynomial functions, and I can find complex zeros of polynomial functions. The rational zero theorem says that the possible rational zeros of any polynomial function are in the form of p over q, where p is the constant term a sub 0, and q is the leading coefficient a sub n. So p is the value that does not have a variable with it. Your q value is the coefficient in front of your variable that has the largest exponent. So we need to list all the possible rational zeros of the function. First, we need to make sure that this polynomial is written in descending order. So we have the largest exponent first and our constant value last. This one is written in the correct order. So remember, your p value is your constant, which in this case is 10. Our q value is your leading coefficient, which is 2. Now we need to find the possible factors, and we're going to do p over q. So we're going to do the factors of p over the factors of q. Remember, in this case, our p value is 10, our q value is 2, so the factors of 10 are 1, 2, 5, and 10. Our factors of 2 are 1 and 2. And remember, we're dealing with factors. They can be positive values or negative values. This is why we're putting the plus or minus in front of them. So now we're just going to find all the possible rational zeros. So we're going to take all of our factors of p and divide it by plus or minus 1. Then we're going to take all of our factors of p and divide it by plus or minus 2. So we're going to divide everything by anything that's in the denominator. So if we do 1 divided by 1, that's going to give us 1. 2 divided by 1 is 2. 5 divided by 1 is 5. And 10 divided by 1 is 10. Now we're going to take each of our factors of p and divide them by q. So 1 divided by 2 is 1/2. 2 divided by 2 is 1, which is already on our list, so we do not have to write it down again. 5 divided by 2 is 2.5, or 5 over 2. And 10 divided by 2 is 5, which is already on our list. So our possible zeros, possible rational zeros, for this function are 1, 2, 5, 10, 1/2, and 5 over 2. And these are all positive and negative values. So I could have a positive 1 and a negative 1. I could have a positive 2 and negative 2. If we do this again, remember our p value is the constant. Our q value is the value in front of our leading coefficient. It's the number in front of our largest exponent. So our factors of p are plus or minus 1, 3, and 9. Our factors of 3 are 1 and 3. So if we write out our possible zeros, we're going to take each of our factors of p and divide it by 1 first. So 1 divided by 1 gives us 1. 3 divided by 1 is 3. And 9 divided by 1 is 9. Now we're going to take each of our factors of p and divide it by 3, our other factor of q. So 1 divided by 3 is 1/3. 3 divided by 3 is 1, which is already on our list, so we don't have to write it again. And 9 divided by 3 is 3, which is already on our list. So these are possible rational zeros. So we're going to continue listing all of our possible rational zeros, but then we're actually going to determine which, if any of them, are zeros of our function. And to test to see if they are zeros, we can actually use synthetic substitution that we used in a previous section in this chapter. So we're going to start out the same way. We're still going to find all of our possible zeros first. So we're going to find our p-value, which is 8. And we're going to find our q-value, which is 3. So we're going to find the factors of each of our terms first. Once we have our factors, then we're going to list all of our possible zeros. Again, remember, you're going to take each of the p terms and divide them by each of the q terms and write out all of our rational zeros. Once you have all the possible rational zeros, the next thing you should do is graph the function and try to find at least one of your possible zeros that matches on the graph. And if we graph this, it looks like we have a 0 at x is equal to -2. So we're going to test -2 first. When we plug this in, if we get a 0 as our remainder, we know it's a factor, and then we'll have it factored down one time, and then we can see if we can factor it down a second time. So let's try -2 first. Remember, when we're using synthetic division or synthetic substitution, we take the coefficient in front of each of our variables and write it down across the top. You bring the first term down, so I bring a 3 straight down. -2 times 3 gives me a -6. -6 plus a -7 gives us a -13. -2 times -13 gives us a positive 26. If we add straight down, we're going to get a positive 4. -2 times 4 gives me -8. We add down, that's going to give us 0. So we know that an x value of -2 works. Remember, when you put it back in the parentheses, you change the sign. So since this was a -2, we put it in the parentheses. That gives us an x plus 2. And then we're left with 3x squared minus 13x plus 4. Now, if you look at the graph again, we have another possible 0. It looks like we have a 0 around the value of 4. So if we try 4, remember, when you're trying a new one, we can just plug it into this part instead of the original. So this will help us break down or factor our polynomial even farther. So let's try 4. So we have across the top 3, -13, and 4. Those were our coefficients from when we got done factoring the first time. So if we bring our 3 straight down, 4 times 3 gives us 12. If we add down, that gives us a -1. 4 times -1 is -4. We add down, that gives us 0. So from the first time, we knew we had x plus 2. Then we just divided by a positive 4. Remember, change the sign when you put it in the parentheses. So that gives me a factor of x minus 4. And then we get done here. This was x squared, so we're left with x to the first. This gives me 3x minus 1. So if this is how we are factored down to the farthest, our zeros would be, if we pull the 2 out, this is going to give us x is -2. If we pull out the 4, this is going to give me x is equal to positive 4. And if we set 3x minus 1 equal to 0, take the 1 to the other side, that gives me 3x is equal to 1. Divide both sides by 3, you will get x is equal to a positive 1/3. And if you notice, all of those values are in the list of possible zeros. A lower bound is an x value, a, where all the zeros are greater than the value of a. An upper bound is an x value that we're going to call b, where all of the zeros are less than b. So if we were to draw a graph of this, if here is our function, remember our zeros are here, 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 and here. A is going to be a value where we can guarantee all of our zeros are greater than that value. And B is going to be a value where we can guarantee all of our zeros are going to be less than that value. Now we know we have a lower bound if the last line of our synthetic division is alternating between positive and negative values. And we know we have an upper bound if the last line of our synthetic division is all positive numbers. So we need to determine an interval in which all of the real zeros of the polynomial must lie. We're going to explain our reasoning using the upper and lower bound test, and then we are going to find all of the real zeros. So first thing you need to do is you need to graph your function on your calculator, and you need to estimate where you think all of your zeros lie. If you look at your graph, it does look like all of your zeros are going to be between -1 and 7. But we actually have to test that to see if that is our lower bound and our upper bound. So we're going to do synthetic division with -1, and then we're going to do synthetic division with 7 to see if they are the upper and lower bounds. So -1 times 2 gives me -2. If we add down, that gives me -13. -1 times -13 is a positive 13. We add down, this gives us 15. Multiply, -15. If we add down, gives us a -59. If we multiply, becomes positive 59. We add down, we get a positive 35. Now if you notice, our terms alternate. We have positive, negative, positive, negative, positive, and we do have a remainder. If our values alternate at the bottom like that, we do know this is a lower bound. So we know we have a lower bound of x equals -1. Now if you would have tried x is equal to -2, it's still going to alternate. So that's still going to be a lower bound. We do know everything has to be above that, but we try to keep it as close to the zeros as we can. So we do have a lower bound of -1. Now we're going to try and check for our upper bounds. To do this, we think it's 7, so we're going to do synthetic division with 7. So if we bring our 2 straight down, 7 times 2 gives us 14. If we add down, that gives us 3. 7 times 3 is 21. Add down, we get 23. 7 times 23 is 161. If we add straight down, that's going to give us 117. And 7 times 117 is 819. And if we add that straight down, we're going to get 795. Now, if you notice, all of these values are positive, and we do have a remainder. So since they're all positive and we have a remainder, we do know this is an upper bound. So the next thing we need to do is to find all of the zeros. So if we look, we need to find our p-value. Remember, p is your constant, so our p is 24. Our q is your leading coefficient, which is 2. So we find the factors of p and put them over the factors of q. Our factors of p are 1, 2, 3, 4, 6, 8, 12, and 24. Remember, you have the positive and negative values of those numbers. And our factors of 2 are 1 and 2, both positive and negative. So if we list out our possible zeros, we take each of our p values and divide it by each of our q values. So our possible rational zeros are 1, 2, 3, 4, 6, 8, 12, and 24 if we divide by 1. If we divide by 2, we have 1/2 and 3 halves because the rest of them were already on the list. 2 divided by 2 is 1, 4 divided by 2 is 2, so on and so forth. Now again, we're going to look at our graph and we're going to find any possible zeros we think we have. And if we look at the graph, it does look like we have a 0 where x is equal to 6. So let's test that one first. So if we bring our 2 straight down, 6 times 2 gives us 12. Negative 11 plus 12 gives us 1. 6 times 1 is 6. If we add down, we get 8. Multiply, we're going to get 48. Add down is a positive 4. 6 times 4 is 24. And that does give us 0. So we do know that one of our zeros is x. Now if we look at our graph, we do have another possible 0 at negative 1/2. So if we test that value, remember when you test the second one, if the first one worked, you can just use your quotient from the first on the second one. So we're going to use that 2, 1, 8, and 4. So negative 1/2 times 2 gives me negative 1. Bring that down. That's going to give me a 0. Negative 1/2 times 0 is 0. If we bring that straight down, we're going to get 8. Negative 1/2 times 8 is going to give me negative 4. And if we bring that down, we get 0. So we do know x is equal to negative 1/2 is a 0. Now we are left with 2x plus 8 is equal to 0. So from this quotient down here, we are left with 2x squared plus 8 as one of our factors of this polynomial. So if we set this equal to 0 to try to find any other x values, first thing we can do is divide everything by 2. So this is going to give me x squared plus 4 is equal to 0. If we take the 4 to the other side, we're going to get x squared is equal to a negative 4. And then we would have to take the square root to get the x by itself. Since this is a negative 4, we cannot take the square root of a negative number and get a rational number. So we do not have any more rational real zeros. So we know our lower bounds is x is equal to negative 1. We know we have an upper bound of x is equal to 7. And our rational real zeros for this function are x is 6 and x is negative 1/2.